Hello everybody, thank you for tuning into this talk, the title of which is Even Threads Are Now Virtual, Past, Present and Future of Concurrency in Java. My name is Miro Cupak and I'm with a Toronto-based company called DNA Stack. Our mission at DNA Stack is to improve lives of people affected by genetic disease, and we do it by making standards and technologies for discovery, sharing, and analysis of biomedical data. If health tech is something you're interested in or curious about, feel free to reach out to me. I'm very passionate about this topic and always happy to connect and talk about it. If you want to reach out, here's my Twitter handle in the corner here. In this session, we're not focusing on the domain. We're focusing on the underlying technology stack, which in our case is, of course, Java. In particular, we're talking about what APIs and constructs Java provides for concurrency, how the concurrency model has evolved over time, and what the next step in this evolution is. One thing I find about concurrency is that whenever it's talked about, the concept and the theory behind it is really the topic of the conversation. Critical sections, thread safety, Java memory model, concurrency versus parallelism, that sort of thing. But as a developer, I just want to dive in. I want to know what the APIs are and how do I actually use the constructs in my code. So today, we're going to take a very pragmatic approach to concurrency. In fact, to the level that I've actually only prepared 2 slides for you, and you're looking at one of them. I like learning through examples, so the rest of this talk is going to be all live coding. And I'm going to write my examples in JShell, because I find it's nicer for demonstrating sort of isolated things when you abstract away from all the magic IDEs do for us. So let me switch to my terminal here, and let's get started. The basic unit of concurrency in Java is a thread, represented by the thread class. Interestingly enough, this is something that has been available since the very first version of Java. Even in Java 1, 25 years ago, we had the runnable interface and its implementation, thread. So we could easily do something like this. I can create a new thread, which actually takes a runnable here. So I'm just going to do a quick lambda. Of course, lambdas weren't available back then, but we can take advantage of them now. And I'm just going to print out a simple string. Let's say hello JFuture, and let's call this thread t. And now I can start a thread, and you can see that we get the right output. So that's very nice. That was a big deal at the time, because we had this abstraction in the JDK, so we no longer had to write native code to handle threads. JDK 1 was in fact tiny. We were really talking 200 classes or so, and a big chunk of that was AWT and its UI components. Java Lang was only about 20 classes at the time, plus some errors and exceptions. So the fact that thread was present in the very first edition of Java really shows how core the concept is to the Java platform. So what could we do with this construct in the early days of Java? Well, not much actually. If we take a look at the thread API here, we can see that there are a few methods here. Most of these have been here since the early days. It's quite a strange API because different parts of it withstood the test of time to varying degrees. Some parts are now deprecated and others are just confusing. We saw the start method in action, which is sort of the main method you would want to call here. Another really commonly used method is the method current thread, which, as the name suggests, gives you a reference to the thread you're currently in. For example, like this. And let's call this t. Then we have a few methods to extract some information about the thread. Of course, the most well-known one and the one we've all used is getStackTrace. So I can call getStackTrace here, and this returns an array of stacktrace elements representing the stack of this thread. Like we said, exceptions and debugging context is tied to a thread. We also have a method called getID here, which just returns the identifier of the thread. Threads in our application are actually numbered sequentially by the JVM. That's why the ID on the main thread is actually 1. We also have a method called getName, which is a bit more interesting. This method returns the name of the thread. In this case, we're just on the main thread. But this implies that we can actually name our threads, which can be handy if we have many of them. And this is actually quite an underrated feature, which I wish people used more often. It's very useful for logging and debugging purposes. Actually, not only we can name the threads, but every thread has a name. If we don't specify one, it will be generated for us. The easiest way to specify one is through the constructor. If I go back to my constructor here, I can just give it a name, let's say worker, and let's also modify this printout to actually, for the thread, to print its own name. So I'm going to do a thread, I'm going to use the current thread method and get name, and this should be just fine. Let's try it out, and you can see that it prints out worker. So we saw that you can start a thread using the method start. But confusingly enough, there's another method here which looks like it might start a thread, and that's the method run. But if we take a look here, if we actually call the method run, you can see that we get a very different result. Because you see, this is the run method from the runnable interface. And if we call it, it doesn't actually start a new thread to execute this runnable. This is just a normal method call now. So the thread executing this is, as we can see, our main thread. So if you call run by mistake, it can be quite a tricky bug to hunt down. Start is the method that you're most likely looking for here. There's actually a similarly confusing situation when it comes to stopping a thread as well. You might be tempted to just call thread stop, but that actually is deprecated and inherently unsafe. The closest thing we have to stopping is actually interrupt, and ideally this would be coupled with some handling in your run method. Of course, it's not the same as stopping. This is sort of politely asking a thread to stop, and it's up to the thread to decide if it wants to continue or actually stop. But this is what we have in the JDK. Same for pausing, actually. We're all familiar with the method sleep, which pauses the thread for the given number of milliseconds, let's say 2 seconds here. But suspend and resume are actually deprecated, as you can see here. Of course, wait and notify on an object are fine as well as sort of the basic synchronization constructs. And finally, we also have a method join, which waits for a thread to terminate. So we can just call it here, and of course the thread already terminated. There is actually one more thing. We've covered what you can do with individual threads, but if you have many of them, you might benefit from a construct simplifying thread management, like thread groups. Thread groups, as the name suggests, provide a simple way of grouping threads. You can create a new group, just like this, and we can give it a name, let's say group, and let's call this TG. Now, if we take a look at the API here, not much going on, really. And most notably, we don't actually have methods for adding and removing members here. To add a thread to a group, you need to specify the group when you create the thread. So if I actually go back to my constructor here, I can add a group here at the beginning of this constructor, and this now creates a thread in the given group, which we can verify here. You can see this is now our custom group here. There's a reason why we add threads to groups this way. Group assignment is actually permanent. You can't just move threads between groups. And actually, every thread needs to be assigned to a group. If you don't name one, you get assigned to a default one. There's a group called system for the JVM threads, like system threads, and it has a child group called main for our application, which starts with a single thread running your main method. We can actually see that here in JShell. If I obtain a reference to my current thread and take a look at the thread group here, you can see that it was automatically assigned to a group called main. And this is actually a hierarchy. Thread groups are also assigned to thread groups, so you can end up with a tree of threads, if you will. And this is useful, sort of a basic thread management construct here. I want to mention one other thing here, which was actually added in Java 2, but really became useful in Java 5 with the addition of generics. And I want to mention this because it's one of the most widely used concepts related to threads today. That concept is, of course, thread local. As we started relying on threads more heavily, it became pretty clear that we needed a way to store data in the scope of a single thread, which is a use case not really captured by other Java primitives. And thread local is the construct that allows us to scope variables that way. So unlike regular variables, thread locals allow us to give each thread its own independently initialized copy of a variable. So it's a perfect feature for storing thread state. It's actually really simple to use. We have a class called thread local here, and I can just create a new thread local very easily. This class only had a handful of methods. So let's just make a thread local of type string here, and let's call this TL. Now we can set the value in this thread local, in our case a string of course, so let's use our favorite one here. And this importantly sets the value for the current thread. Finally, we can extract the value. And that's pretty much all there is to know about threads, really, as we've had them in Java for about 25 years. OpenJDK currently provides a single implementation of threads, which is a relatively thin wrapper around operating system threads. So when you create a thread in Java, a new OS thread is actually created to back it. And this gave us simplicity initially, but as you can imagine, it results in certain inefficiencies. The operating system doesn't know what kind of workload the thread is executing, what language it's written in, or how the language manages the stack. So the OS must go for the very conservative and robust approach that gives you a good compromise across all the possible implementations, which in turn makes Java threads pretty heavyweight. Scheduling also is a compromise across all the use cases, so you're not getting optimal cache locality. And context switching needs to go through the kernel, which is also relatively slow. And because every task consumes a thread, the number of tasks we can handle is bound by the number of threads we can handle, which on a regular machine would be in the thousands, nothing crazy. So threads themselves became the bottleneck. And there's certain irony in that, right? The reason threads were introduced in the first place was because hardware was the scarce resource, and threads were the lightweight mechanism at the time, allowing us to share this scarce resource. Yet over time, threads themselves have become the scarce resource, and soon we needed another abstraction. So what do? Well, the same thing we always do when we have an expensive resource. We try to share it. And how do we share threads? Threadpools, which brings us to Java 5. The idea with Threadpools is that instead of spawning a new thread for every incoming request, we have a pool of threads. So we typically create such a pool at the start of the application, and then when the request arrives, we borrow a thread from a pool, run the task on it, and then return the thread back to the pool when we're done. This gives us some level of sharing. Java 5 introduced three useful interfaces in this aspect: Thread Factory, Executor, and Executor Service. Thread Factory is pretty much what you would expect. It's an implementation of a very common design pattern in Java, and it's basically a low-level thread management construct, essentially an object that allows us to create many threads of certain configuration on demand. I'll just use the default thread factory here, reach into executors, call the default thread factory, let's call this TF, and now I can use this factory to actually create a new thread, which, as we all know, requires a runnable, so I'm going to use a favorite runnable here, system out print line hello JFuture. And let's just start this immediately as well, and we can see that it works. So that's Thread Factory. Executor is an object that executes tasks, runnables. It's a way of decoupling task execution from thread use and how each task will be run, scheduling. It's a higher level construct than a thread factory. It's actually something that would typically use a thread factory to deal with threads. Executor service extends executor, and it's sort of a more extensive framework for execution of tasks or runnables. All the implementations of the executor interface in the JDK actually also implement executor service. So executor service is the more useful construct here, and in practice, this is what we really mean when we're talking thread pools. So how do you use it? Well, I can create a new executor service here. Let's just say I'm going to use a new fixed thread pool, let's say consisting of 3 threads, and let's call this E. Then I can call the method execute here, which again requires a runnable. Let's just use our favorite one, system out print line hello JFuture, and this works just fine. And this actually gives us a lot, right? With push scalability further, we can now relatively easily reuse threads. But this isn't really how threads were meant to be used. This is basically a workaround for improving concurrency. So what are the problems that we might encounter? Well, we saw that thread locals are an important construct with threads. And with thread pools, our thread locals might leak. Let's say one of our tasks takes a thread, right? It creates a thread local and then forgets to reset it. Then a different task gets the same thread and can now read those unrelated thread locals, which can cause surprising consequences in highly concurrent applications. So it's actually a good practice to reset thread locals yourself before and after execution. We also saw the methods for interrupting a thread, and we can now encounter synchronization issues with interrupts. Let's say we have a task that's been running for too long for whatever reason and we want to cancel it. To do that, we need to interrupt the thread it's been running on. But because threads can now be shared, maybe you trigger the interrupt, but by the time it's in effect, the task has already finished and the thread is now running a different task and you interrupt that one. And that's something you as an application developer need to think about. There are complexities with interrupts that are not covered by abstractions in the JDK. And finally, thread pools are still not efficient enough. Even though we use a pool, we run a task start to finish on a single thread, right? So the number of tasks we can run in parallel is still bounded by the number of threads we can handle, which, as we've established, is not high enough. So how do we push scalability even further? Well, we notice that while a task is being processed, it's actually only performing computation on CPU for a relatively small amount of time. A lot of its time is actually spent waiting for I/O. So what if, while we wait, we return the thread to the pool, and a different task can reuse it before our task is actually terminated? That allows us to have more active tasks than threads, which brings us to asynchronous programming. Java 5 took the first step towards asynchronous programming. Together with executors and executor services, which we've already seen, it introduced 2 other very useful interfaces, Callable and Future. Callable is kind of like a runnable, which we've seen already, in that it's a representation of a task, and it's a task that returns a result that may throw an exception. And while runnables can be run with threads directly, callables can only be run with executor services. Future is simply future result in a synchronous computation. And this is how they work together with executor services. I'm going to use the executor service that I have from before, and I'm going to use it to submit a task, which in this case, I'm going to use a callable. So let's just do a quick callable here. Let's just say hello JFuture, and this returns a future, which I'm going to call f. And you can see that the method returns immediately, and the future is not completed. So this is asynchronous. Of course, it completes very quickly. It's a very simple lambda. So if I take a look now, you can see that the future is already completed. And we can actually use the get method from the future interface to extract the value in this future. Now this seems simple, but it actually gives us a pretty sophisticated synchronous system, and it allows us to push concurrency in Java a bit further. But as you can imagine, as time went on, this still wasn't efficient enough. Pretty soon, we needed more. And the help came with Java 7, which introduced the fork join framework, and most importantly, fork join pool. Well, the key assumption behind it is that newly created tasks are more likely to have their data in a closer cache than older tasks. So maybe we should run those on our CPU and schedule old ones for other CPUs. And this is how it works. When I create a task, it goes in the queue. Every thread has a queue it needs to do. When the thread is ready, it says, hey, I'm ready, do we have any tasks in the queue? And it takes a task and executes it. When a task needs to do more work, it adds more tasks to the local thread queue. So the thread keeps pulling tasks from its local queue, which means ideally we're not corrupting our cache. So how do we scale this across threads? Well, if another thread is out of tasks, it does what's called work stealing, where it grabs a task from the bottom of someone else's queue. And the expectation is that the bottom of the queue is far enough from the cache that moving it to a different CPU will have the least performance impact. And it turns out that this works really well for synchronous computations. We get good single-threaded performance, and as we're adding tasks, we get pretty good sharing across CPUs. In fact, fork join pool works so well that it is what pretty much all the higher-level components relevant to concurrency in the JDK use under the hood. If we wanted to use it directly, a very simple way of doing that is just by modifying the example from before. If I go back to my executor service, I can just get the fork join pool here, let's say just the common pool, and then everything else I can execute the exact same way. I can submit a task, I can extract a value, and it works just fine. Of course, this is a very primitive way of using the fork join pool. I'm not really benefiting from it here, but it's just for demonstration purposes. So with futures, we're asynchronous. With fork join pool, we can do asynchronous very well. But as you can imagine, time went by, we needed to scale more and more, and at some point, this again wasn't enough. So we took a look at this framework and thought, what are the issues here? Where could we optimize even more? And the problems we have are that futures are hard to compose. What you see in practice, when people are using futures, when they try to coordinate multiple tasks, they often do it by busy waiting. So they're iterating over their tasks, checking, is this done, is this done, is this done? And when all the things are finally done, you schedule the next task that depends on the previous tasks, which obviously wastes resources and it makes a block on the main thread. The get method that we had to call here to get the value from the future is actually also a blocking call. So I can run things asynchronously, but to get the result, I need to block. But as it turns out, Java 8 helps us with this quite a lot by introducing Computable Future. Computable Future is basically a framework for primarily non-blocking asynchronous programming in Java. It's built around a class called Computable Future, which, as the name suggests, is a future that may be explicitly completed, so it can set its value and status. And when I say it's a future, I mean the class literally implements the future interface we've just seen. It also implements an interface called Completion Stage, also introduced in Java 8. And Completion Stage is a representation of a stage in a computation. So basically, we use Computable Futures to model tasks in a bigger, primarily asynchronous workflow, and we have APIs to create dependencies between the tasks and chaining them. In other words, Computable Future addresses several problems we had with futures. It makes tasks easy to compose, it allows us to do so in a non-blocking way, and automatically uses the fork join pool behind the scenes, so it actually performs pretty well. So how does it work? Well, the basic API is actually relatively simple. I can create a new Computable Future, let's say of type string, and let's call this CF. And now I can complete this feature successfully with a value, in our case that's a string, so let's just say done. And now I can use the get method that we already know to extract the value, and of course it's the string that I completed it with. So what happens if I don't complete it? Well, let's try this. Let's reset here, and let's just call the get method directly. And you can see that nothing happens. Because remember, this is the standard blocking call from the future interface, so it's going to block until somebody else completes the future from a different thread. Aside from completing the future normally, I can also complete it exceptionally. If I call complete exceptionally here, this needs a throwable, so let's just give it, let's say, a new illegal state exception. And now if I call the get method here, it actually fails with the exception that I gave it. So that's the basic functionality. I can complete a future normally and exceptionally. What else can I do with it though? And this is where things get more complex. Computable Future is a big class, almost 3,000 lines of code, and quite a few methods, quite a few public ones as well, actually. If I remember correctly, there are 52 methods plus overloading. And a few of them come from the future interface, as we've seen, but the vast majority come from the completion stage interface, which has a whopping 38 methods. So yes, probably not the best API design, but there's actually a system to these. The reason we have so many methods is because there are 3 categories of what we want to express in the API, and we need to express all the possible combinations, which gives us 36 methods. The 3 categories are what kind of a task this is, how do I process it, what kind of an operation it supports, and where, what thread can it execute on. As for the task, there are 3 types. It can be a runnable, it can be a consumer, or it can be a function. As for the operations, we can chain them, as in execute one after another. We can compose them, as in function composition, or we can combine 2 of them using AND or OR. And as for the thread it can run in the same executor as the caller, in a new executor passed as a parameter, or in the common fork join pool. So for example, and let's take a bit of a more realistic example, I'm going to create the futures in a different way and do everything asynchronously in a single pipeline, which is how you often see this done in sort of real life code. So I'm going to start by creating a completable future, and I'm going to do this asynchronously. I'm going to call supply async, and let's just give it quick lambda here, going to return hello. Then I'm going to call then apply async. And the naming pattern of these methods actually tells me, what's going on here. Supply async, the name tells me that I'm going to need a supplier to generate my task, and I'm going to do this asynchronously. So not in the caller thread, but either in the executor given as a parameter, or I will let the fork join pool decide. Then apply async, then tells me that the operation is basic chaining. Apply tells me that my task is a function, and async, we've already discussed, I'll just use the fork join pool. So this now needs a function, so let's just give it a quick one here. Let's just, take the string from the previous lambda and append something to it. Let's say something like this. And finally, I'm going to call then accept async, where the name tells me, okay, the operation is chaining again. It expects a consumer as the type of my task. And again, I'm going to do everything asynchronously. So let's just give it a quick consumer here, just a quick method reference. And you can see what the output is here. So you understand now what the system is, right? Why we have so many methods and how the naming works. And this is sort of the simplest basic pattern you can use with computable futures. It's asynchronous sequencing. So it's about creating that basic dependency, ensuring that one task runs after another. But it shows a key property of the Computable Future API. Almost anything that you do to a completable future produces another completable future, which gives you this fluent functional API to model your workflows. And we've really just seen the basics, and I think you can already tell that this is a very complex model. Completable futures get us very far, and they address a bunch of issues that we have with futures, right? We can now compose them easily, and we don't have to blog on the main thread to coordinate. We can just tell it, okay, run a dependent task when our task is done. This is a very important construct in the JDK that everybody should know about. This is just the way to do asynchronous in Java. But it comes at a cost, and the cost is not low. You can see that even with such a simple example, that the API is very complex, and the code is relatively hard to read, write, and maintain. Another issue is loss of context. We're obviously using threads in the background here, but they're hidden from us. We no longer have associations between tasks and threads, right? To get the efficiency, we split our tasks into smaller stages, we return threads to the pool frequently, things move in and out of the pool all the time, and there are no guarantees that different stages of our task continue on the same thread, which of course increases complexity. And this lost context is actually a real issue, because as we said at the beginning, Java depends on this context, right? When we get an exception, we're given context through stack trace tied to a thread. So now we're seeing only stuff relevant for a stage rather than the whole task. Similarly, debugging is tied to a thread. And profiling is hard as well. So how do we solve this? What if we could code in a synchronous way, but get the scalability of asynchronous? In other words, what if we could lower the cost of threads to a point that we could have so many of them that they're no longer a scarce resource? And that's what Project Loom brings to the table. Project Loom is experimental, but a very, very high impact effort, which will quite substantially change how we do concurrency in Java. It's a Java effort, but it's not in the JDK yet. It isn't even planned for any soonish release as far as I know, but it is under heavy development, and it has been under development since 2017. And really, things are being changed constantly. The information that's out there often gets out of date pretty quickly, but here's what we know right now. Project Loom really took a step back and said, okay, concurrency has gotten pretty hard, as we've seen today. Let's get back to the roots. Let's take a look at threads and create a much more efficient version of them so that we don't need these complex workarounds like Threadpools and futures. Project Loom does this by introducing the concept of virtual threads, formerly known as fibers. Virtual threads are lightweight threads which are inexpensive to create and block. They are managed by the Java runtime and implemented in user space, unlike regular threads, which wrap operating system threads. So what you're getting by having Java manage them is a lot of efficiency thanks to the additional knowledge Java has. For the OS, as we said before, a thread is more of a black box. The OS doesn't know what kind of workload the thread is executing, what language it's written in, and how the language manages the stack. So the OS must go for a very conservative and robust approach that gives you a good compromise across all the possible implementations. But if Java manages its own threads, it knows a lot more about what they do, so it can represent them in a much more compact way and adjust scheduling accordingly. Virtual threads are threads. So to create one, I'll start with the thread class that we already know. Now, unlike regular threads, there is no public or protected constructor for virtual threads. By design, so as not to have to deal with subclasses. Subclasses of thread cannot be virtual. So instead, I'm going to call a method here, and the method is called startVirtualThread, which, as you can imagine, takes a runnable. So I'm going to use my favorite runnable here again, system out println hello JFuture, and that's just it. And you can see that this created and executed a virtual thread, and we have the output right here. We don't have to start threads directly. If we want more flexibility, there's a builder as well. So I can just call thread, give me a builder, let's build some virtual threads here, and let's give this a task. Again, my favorite runnable, as always, system out println hello JFuture, and let's call build, and actually let's call this whole thing T. And we can see that this indeed is a new virtual thread. We can actually even check this here. There's a new method for this. If we want to, indeed this is virtual, and now we can start it, and of course executes just fine. This builder here is actually a really nice addition to the thread API. It's not specific to virtual threads. I can use it with regular threads as well. It's kind of an overall convenience feature that just happened to be added as part of Project Loom. The things that I had to do with threads through constructors and setters before, I can now do with the builder. For example, if I wanted to name the thread, I can just go back to my builder here and just add something like name worker, and we can see now we have a thread that's actually called worker. So naming works just fine with virtual threads as well, and it could be actually very useful since we have so many of them. But there are many limitations as well. For example, priorities are just ignored. If I go back to my builder and I try to change the priority of my thread, let's just say we give it minimum priority here. But as we can see here, if I try to extract the priority and compare it to the normal priority, it's actually going to be the same. So the priority of a virtual thread is always normal priority. Thread groups are not supported either. If I go back to my builder here, and I'm going to remove this priority and replace it with a group, and let's reuse our previous group, you can see that this doesn't actually work. To be exact, when I say that thread groups are not supported, what I mean is that I cannot specify a custom group. But to be consistent with regular threads, where each of them needs to be assigned to a group, they do actually have an implicit group. So if I take a look here at the thread group, you can see that there is a group called virtual threads for these virtual threads. Many methods that we've seen are also missing support, especially the ones we've described as confusing. So run method on a virtual thread actually does nothing. The deprecated methods like stop, suspend, resume, they just outright throw an exception. They're just not supported. The main methods that we saw, like get stack trace, sleep, current thread, they are of course all supported and pretty commonly used. So let's just try one of them as an example. If I go back to my builder here, I'm going to change this printout to just print thread, current thread, get name, and this, of course, works just fine. Importantly, thread locals are supported as well. These are obviously used very frequently, so if they weren't supported, it would be a substantial barrier in adoption. We can demonstrate that quickly here. I'm just going to go back to my builder, and I'm going to modify this task here. All I'm going to do is actually create a block, and in this block, I'm going to create a thread local. So let's just make a thread local of, let's say, type string. Let's call this TL, make it a new thread local, and then let's set the value in this thread local to our favorite string, hello JFuture, and hopefully this just works. Let's try to start it here, and no problems. The good thing about this is that in some way, thread locals work better with virtual threads than they do with regular threads. Because remember, one issue that we had with Threadpools was the potential for thread locals to leak because we were sharing threads, which is no longer an issue here because virtual threads are so cheap that we don't actually need to share them. There are, however, other complications here as well. The reason Loom works is because virtual threads are so lightweight, right? To a point that having thread locals could actually substantially increase their footprint. So if you wanted to keep them really light, you can actually disallow thread locals through the builder here. So if I go back, I can just add another step here, disallow thread locals, and now if I try to execute the thread, you can see that I'm getting an unsupported operation exception. It should also be noted that inheritance is tricky as well. Thread locals can be inherited between parent and child threads. With Loom, we're actually encouraging creating new child threads frequently for various stages of our computation, like each HTTP request to different microservices, that sort of thing. So we might rely on inheritance even more often now. But thread locals are mutable, as we've seen, and as such, not safe to share between threads. So they must be copied when you're creating a new thread, which creates performance overhead, again multiplied by the very large number of threads that we have now. So alternatives to thread locals are actually being explored as part of Project Loom, and one of these alternatives are scope variables. Scope variables are immutable and have a smaller scope, just a code block instead of the whole thread. These scope variables have been prototyped in Project Loom. It's a very early prototype. There's actually just one class with absolutely no Java docs, so it's likely to change, possibly disappear, and it's also possible that the implementation will be deferred to a future Loom release, not the initial one. But a simple example would be something like this. I can create a new scope variable here, let's say of type string. So I'm just going to do scoped for type, and let's give it a string class, and let's call this s. Now I can bind the value to this variable. So of course I'm going to use my favorite string here. And now this value is in effect for the duration of the scope. It should be noted that this is still immutable. I can't mutate it, but I can bind a different value to it in the different scope. And once you leave the different scope, you have the old value again. So I could, for example, have a block in a thread defining the scope, then create a new thread in that block, share the value in the scope with that thread, it supports nesting that way, then bind it to something else in the child thread, and when I return to the parent, it will have the original value. There are some language changes necessary to demonstrate this behavior in a meaningful way, but for now, I can simply extract the value here using the get method, just so that we can see the API. What's also important is that not just the bare thread, but Java 5 features that we saw are supported as well, to an extent. For example, thread factories. In fact, they're not only supported, it's actually much easier to create them with the new builder. I can obtain a builder here, tell it to build virtual threads, and I can just call factory, and this gives me a nice thread factory here. The importance of this being supported is that this is sort of an integration point with other APIs we're now used to using, such as executor services. If we take a look at the factory methods for executors, here pretty much all of them accept a thread factory as an optional argument. So you can give them a factory to create their threads, and because we now have a factory for virtual threads, they all automatically work with virtual threads. So you can migrate from regular to virtual pretty easily. I can reproduce our executor service example from before, now with virtual threads like this. I can create a new thread executor. I can give it my factory from before, and let's call this E, and now I can submit a task, which of course is a callable here. So again, my favorite string for consistency, and let's call this whole thing F. This of course returns the future, and now I can extract the value from the future. So it's a simple executor that starts a new thread for each task. And notice that this really is the same as the example from before Project Loom that we used. The only difference is the thread factory here. So very easy drop and replace. For convenience, we actually now also have a new executor contributed by Loom, which is actually just called new virtual thread executor. And again, I can use it interchangeably. I can just rerun the previous example, and this is all going to work exactly the same way. Since we're virtual threads, we don't typically need any sophisticated constructs like Threadpools because they're so cheap. It's a very simple executor actually, it just creates a new virtual thread for each task. Loom actually provided another enhancement to executor services that's very cool. Executor service now extends auto-closable. Pretty much all the constructs that represent external resources do that in the JDK now, so this just makes complete sense. The advantage in practice is that we can now use executor services in try with resources statements. So relying on our example from before, I can do something like this. I'm going to create a new try with resources. Inside, I'm going to create a new executor. Let's say executors. Let's use the first example here. I'm going to give it my thread factory. And here in the body, I can just submit a couple of tasks. So maybe something like this. Quick lambda, system out, print line, hello. And let's make another one just to make it more interesting. JFuture here. And now what this does, you can see that it actually creates a new executor using our thread factory. This executor creates a new virtual thread for each task we give it, no pulling or anything because we're talking virtual threads. Then we give it 2 tasks to execute, and when they're done, we clean up. The interesting thing about this is that the current thread will block, waiting for all the tasks and their threads to finish. In other words, when we exit the try with resources, all the tasks and their threads are guaranteed to have completed. And this is very interesting and a very powerful invariant. This concept is known as structure concurrency. There's literature available about this. I'm not going to go into too much detail. But basically, structure concurrency means that the runtime behavior mirrors the structure of the code, which makes it easier for us to reason about the code. Our code is arranged in blocks, and based on these code blocks, we can see where each thread starts and finishes. So implicitly, every thread has a parent that blocks until the children terminate. There are actually more similarities between virtual threads and asynchronous programming with completable futures, including scheduling. With virtual threads, we're not scheduling on the CPU directly, but we schedule virtual threads onto regular platform threads, which we call carrier threads. So like with asynchronous programming, we do end up scheduling, regular kernel threads ultimately, but we abstract that through familiar threads rather than some new constructs. From application perspective, carriers are sort of isolated. We can't access them. For example, the current thread method we saw will refer to our virtual thread, not the carrier. Only the scheduler interacts with the carriers and mounts virtual threads onto them. Similarly to completable futures, the default scheduler we use here is the fork join pool, like we've seen before. By default, the number of carriers is equal to the number of cores on your machine, but it is configurable at the JVM level through a flag, similarly to, for example, parallel streams. If you wanted to specify a custom scheduler, you can specify it when you create a thread in the builder. So if I go back to my builder here, I can just go here and use some auto-completion, and you can see that this does actually take a scheduler in the form of an executor. So for example, if you're not happy with a global number of carriers, you could implement custom schedulers that delegate to different numbers of carriers based on the tasks. And as we've seen, executor is a very simple interface. It only prescribes one method, execute, which takes a runnable. And there's even an interface sort of extending runnable to represent the task for our virtual thread, and that interface is called virtual thread task. So this actually allows us to distinguish between virtual and regular tasks so that we can deal with blocking and resuming on carriers. One final thing before we wrap up here, Loom also introduces the concept of continuations. Strictly speaking, this is a low-level construct that we as application developers don't even need to be aware of, but it is currently a part of the public API, so I wanted to mention it at least briefly for completeness. The idea is that running virtual threads requires two things: a scheduler and continuations. The scheduler decides when and where we run, which carrier thread we mount onto. The continuation decides what we run. It's a representation of computation that can be paused and resumed. So it's basically a wrapper of a runnable that can pause and continue from where it was paused. And it's important to keep this concept separate, because this allows us to reuse ordinary Java schedulers for virtual threads, as we've seen. Continuation needs two things. It needs a scope, and it needs something to run in the form of a runnable, of course. It has two important methods, run and yield. When you call run, the continuation starts running the runnable until it calls yield. When the continuation calls yield, the run method returns to the caller. But the next time you call run, it will continue from the last point the continuation yielded. For example, let's start by creating a scope. So I'm just going to create a new continuation scope. Let's give it a name. Doesn't really matter. Let's just call it a scope. And let's call this whole thing CS. We can now create a continuation. So I'm just going to do a new continuation. And this needs a couple of parameters. It needs a scope and it needs a runnable. So I'm going to give it my scope and I'm going to give it some runnable. Let's do a slightly larger one. Let's make this a multi-line lambda. First, I'm going to print a string, just so that I have a statement here. Then I'm going to yield continuation yield to my scope, and then I'm going to add some more statements, system out, print line, JFuture, just like this. And let's call this whole thing C. So now we should be able to run this continuation. So I'm just going to call run, and you can see that it executed the first print out, but then nothing happened after because it yielded. It returned to the caller. We can check if the continuation is done here, and of course it's not. There's still more to do, so we can run it again. And now you can see that it actually just continued from this point, and it just executed the second printout. If we take a look now to see if it's done, of course it is. So if we try to run something, we're actually just going to get an exception. To sum up, virtual threads allow us to achieve pretty impressive efficiency. Creating virtual threads is cheap. You can have millions of them without the need for Threadpools in most cases. Blocking is also cheap. You don't need the more complicated asynchronous programming in many cases. You can just be synchronous. And if you want the flexibility of asynchronous programming, you can make it work with virtual threads for pluggable schedulers as well. And that's it for me. I hope you found this talk useful. If you want to learn more about the topic, I'm sure you'll have no troubles finding materials on concurrency in general, but I thought it'd be useful to point out some resources about the emerging Project Loom, because these are actually relatively hard to find. The first link on this slide is sort of the main Project Loom resource. It's a couple of pages on the OpenJDK wiki with links to downloads and such. But unfortunately, the documentation is actually very sparse. The closest thing we have to real documentation is actually this article by Ron Pressler from the Java Platform Group on the state of Loom from earlier this year. This really helped me understand the project, and many of the examples I've shown today were inspired or directly taken from these talks. If you have any questions, I believe there's a Q&A session scheduled for right after this talk, or feel free to reach out to me later. Here's my Twitter handle in the corner here. And otherwise, thank you.